All right, in today's lesson here, we're going to take a look at the projection vector mapping and also the perpendicular projection mapping. So we can take a look here. Our first question here, they want us to find the projection of the vector x1, x2, x3 onto the following vector here. So we have our projection formula here. Now this is derived. You can take a look at previous video going through the derivation or look at your notes. But here's our formula. We want to go ahead and calculate the projection of x onto A. So in this example here, we want to calculate the projection of the vector x onto -2, 3, and -1. Now, because we're choosing an arbitrary vector, we're going to take a look at the image of each of your standard basis vectors using your projection formula. So let's go ahead and calculate this for, in this example, let's go ahead and calculate this for 1, 0, 0, 0, 1, 0, and 0, 0, 1. So go through and do our calculations here. All right, so plugging this in here, we have the following formula. I'm going to go ahead off to the side here. Let's go ahead and calculate the length of this vector here. So this is going to end up being the square root of -2 squared plus 3 squared plus -1 squared. And we're going to get here 4 plus 9 plus 1. And you're going to get root 14. Again, we're squaring that. So when I put that into this equation here, you'll notice your standard basis vector acting on this is just going to grab the first coordinate. So this is going to be -2 over 14 times the vector -2, 3, and -1. So reducing this here, you end up getting as -1 over 7 times -2, 3, and -1. Take a look again. Now we're going to take the projection of 0, 1, 0. And doing that here again, you're going to see when you do your calculation, here you're going to have a 1 here. You're going to be grabbing the second coordinate. So this is going to be 3 over 14 times -2, 3, and -1. And lastly, the projection of 0, 0, 1, it's going to grab the last coordinate. So -1 over 14 times -2, 3, and -1. So going ahead and putting this in matrix form, we're going to get the following here. So, and again, we write this column-wise. So this is going to end up being 2 over 7, -3 over 7, and 1 over 7. And then this is going to, if I reduce this here, you're going to end up getting here -3 over 7. Again, when I'm distributing that in, that'll be 9 over 14 and -3 over 14. And the next one here, this is going to be 1 over 7, -3 over 14, and 1 over 14. And now you can see here I have the matrix representation of the projection of any vector onto -2, 3, and 1. Just a matter of multiplying by some vector here. In this case, x1, x2, x3, whatever vectors you choose, multiply this out, and you'll have the projection of that vector onto our vector here, A. All right, let's take a look at another problem. So in the next problem here, the same sort of idea. We want to find the projection matrix onto the vector 1, 2, -1. And then we want to also find the projection perpendicular matrix to the vector 1, 2, -1 as well. So I want the projection and perpendicular projection onto the vector 1, 2, -1. So let's go ahead and do that here. So same way to go about this. You're going to find out how it acts on each of your standard basis vectors. So just like before, I'm going to have to go ahead and calculate the length of this vector. And I'm going to get, this is going to be 1 squared plus 2 squared plus -1 squared. And I get 1 plus 4 plus 1. And I'm getting 6 here. So now when I go ahead and do my formula, if I let it act on 1, 0, 0, you're going to end up grabbing the first coordinate. So it's going to be 1 over 6 times the vector 1, 2, minus 1. That'll be our first column. Then let's just make some room here. Then I'm going to go ahead and take the projection of 1, 2, minus 1 on 0, 1, 0. That's going to give me 2 over 6 times 1, 2, minus 1. And then we have the projection of 0, 0, 1 is negative 1 over 6, 1, 2, minus 1. And you end up getting this one, and you end up getting this one. Writing your projection matrix, I end up getting here 1/6, 1/3, negative 1/6. Then I end up getting here 1/3, 2/3, and then negative 1/3. And lastly, I get 1/6, negative 1/3, and 1 over 6 as my projection matrix here. All right, now let's calculate the perpendicular projection. So for the perpendicular projection, we're going to go ahead and calculate the perpendicular projection. Again, on each of the standard basis vectors. Well, that's just equal to 1, 0, 0 minus the projection of 1, 0, 0 on 1, 2, minus 1, right? So this is going to be our formula here to calculate the perpendicular projection. So we'll go ahead and calculate this here. You'll notice this is going to be 1, 0, 0 minus, we had just calculated this all the way up here, 1/6 times 1, 2, minus 1. And if I calculate this here, we're going to end up getting here 5/6 minus 1/3 and 1/6. And we continue doing this, so the perpendicular projection on 0, 1, 0 is going to be 0, 1, 0 minus, and again, go all the way up here, grab the next one here. I'm also just write this as a third. I probably should have done that earlier. This will be 1/3. And then times our 1, 2, minus 1. And this ends up being negative 1/3. This will be 1 minus 2/3 is going to be 1/3. And this is going to be 1/3. So we have that one. And then lastly, the projection, perpendicular projection of 0, 0, 1. So you're going to get 0, 0, 1 minus, and the projection vector here was negative 1/6. So watch the double minus sign here. This is going to be negative 1/6. And cleaning this up, I get 0, 0, 1 plus 1/6, 1, 2 minus 1. And doing my calculations here, I'm going to get 1/6, 1/3. And lastly, this is going to be 5/6 for this vector. So go ahead, and these are the columns again. So if I go to calculate my perpendicular matrix here, it's going to be perpendicular matrix on 1, 2, minus 1, writing this column-wise. Going to go ahead and get 5/6, negative 1/3, and 1/6. And the next one is negative 1/3, 1/3, and 1/3. And lastly, 1/6, 1/3, and 5/6. And this ends up being our perpendicular projection matrix here. All right, now that we have our projection matrix and our perpendicular projection matrix, let's go ahead and this is our projection matrix here. The question continues. They want you to find the image on 2, 2, 2, I believe. Yes, the vector 2. They want the vector 2, 2, 2. So we go ahead and grab each of these matrices and just multiply by 2, 2, 2. So let's go ahead and grab this projection matrix here. So I'll grab this here. So let's start off with that here. They want the result of when you take the projection of the vector 2, 2, 2 onto 1, 2, minus 1. And again, because we have created our matrix here, The only thing that I have to do is say, okay, if I'm looking to calculate, essentially they're asking you what is the projection of the vector 2, 2, 2. I want to find this. The only thing I have to do is go to my matrix I've created, my projection matrix, and multiply this by 2, 2, 2. So again, this is a 3 by 3 matrix. I'm multiplying by a 3 by 1. It's going to result in a 3 by 1 matrix. So my answer is going to be a vector, as expected. So if I go ahead and do this here, you're going to end up getting, I guess we can just calculate it separately. So if I go ahead and calculate this, you're going to end up getting here 2 over 6 plus 2 over 3 minus 2 over 6. And for the next one, you're going to get 2 over 3 plus 4 over 3 minus 2 over 3. And lastly, you get minus 2 over 6 minus 2 over 3 plus 2 over 6. And our final answer here comes out to be 2/3, 4/3, and minus 2/3 for our vector here. Now again, if you want, you can factor out the 2/3 out of here. And if I do that, you factor out the 2/3, you can see I get 1, 2, and minus 1 times that vector. All right, let's go ahead and take a look at the perpendicular projection. Again, for the perpendicular projection, again, I want to find, the question's asking, what's the perpendicular projection of 2, 2, 2 onto here? The only thing that you have to do is go ahead and take your perpendicular projection map and multiply this by 2, 2, 2. And again, another option here, what you can do is you can see I can factor out a sixth out of this matrix here. If I take a 6 out of every entry in this matrix, this is going to be 5, negative 2, 1. This is going to be equal, if I'm taking out a 6, this is going to end up being negative 2, 2, 2, and this is going to be 1, 2, 5. You can clean it up a bit and factor the 6th out, and you can see when I multiply this by 2, 2, 2, the 1/6 you take care of at the end. So this ends up being here, you're multiplying this times this. This ends up being, just to go through it, this is 10 minus 4 plus 2. And then this is going to be negative 4 plus 4 plus 4. And this will end up being 2 plus 4 plus 10. And this will be 1/6 times, you can see here, I end up getting 8 as my first entry, 4 as my second entry, and 16 as my third entry. And you can go ahead and distribute the 1/6, or you could factor a 4 out of this whole thing. A 4 will come out of the entire expression, in which case this becomes 2, 1, 4. And you can see this ends up being 2/3 times 2, 1, 4 becomes the vector here. So this is another option that you can do to calculate your perpendicular projection. Or I could have done the same thing here with my normal projection answer. Just another quick observation. Notice that the perpendicular projection vector and the projection vector, if you multiply those two out, they're perpendicular to one another. So it's a good way to check that you're doing your calculations correctly. All right, that concludes today's lesson, just going through projection and perpendicular projection vectors. Thank you.